Hello viewers, in the previous video, we discussed about the standardized protocol stack for IoT and a novel adaptation layer protocol 6LoWPAN which enables IP-based communication in IoT. In this video, we will talk about routing and application layer protocols of IoT. But first, let us understand the term routing and its type in detail. Routing is the ability to send a data packet from one device to another device, sometimes over multiple hops. Depending on what layer the routing mechanism is located, two categories of routing are defined, that is mesh under and route over. Mesh under uses the link layer or the MAC address to forward data packets, while route over uses network layer or the IP addresses. In a mesh under system, routing of data happens transparently. Hence, mesh under networks are considered to be one IP subnet. Therefore, mesh under networks are best suited for smaller and local networks. Whereas in route over networks, the routing takes place at the IP level. The usage of IP routing provides the foundation to larger and more powerful and scalable networks. Compared to mesh under routing, route over routing features the advantage that most of the protocols used on a standard TCP/IP stack today can be implemented. One such route over routing protocol for IoT is the RPL. RPL, pronounced as RIPPLE, is the acronym for IPv6 Routing Protocol for Low Power and Lossy Networks. It is an adaptive routing protocol for IoT and most widely used for route over 6LoWPAN networks. RPL is defined by IETF in RFC 6550. The main features of RPL are energy efficient routing, which means RPL optimizes routing for low power devices, reducing energy consumption by carefully managing data transmission and device wake-ups. Second is adaptive topology, which means its topology accommodates the dynamic nature of IoT networks, allowing devices to join or leave without disrupting the overall connectivity. RPL provides mechanism to support multi-point to point traffic and point to multi-point traffic. Now, we will understand the need for a new routing protocol in IoT. RPL was needed because low power and lossy networks, that is the LLN routers, had constraints on processing, memory and energy. They could use conventional routing protocols like OSPF, RIP, AODV, DSR, etc. They were interconnected by lossy links and the traffic patterns were not simply point to point, but in many cases point to multi-point or even multi-point to point. The routing strategy in RPL is based on destination oriented directed acyclic graph, that is the DODAG. But first let us understand what a DAG is, that is directed acyclic graph. DAG is a directed graph having the property that all the edges are oriented in such a way that no cycles exist. Next is the DAG route. A DAG route is a node within the DAG that has no outgoing edge. Lastly, destination oriented DAG, that is the DODAG, which is a DAG routed at a single destination, that is at a single DAG route, which is the DODAG route with no outgoing edges. Next in the RPL terminology is up. Up refers to the direction from leaf node towards the DODAG route. Then is the down. Down refers to the direction from DODAG route towards the leaf nodes. Objective function. Objective function defines what metrics or constraints to use for finding minimum cost paths in a given RPL instance, like minimize energy, latency, etc. Then we come to rank. So, rank is a scalar representation of the node location within a DODAG instance. The rank must decrease on each path towards the route. It should be computed based on routing metrics established by an objective function. Next is the RPL instance. An RPL instance may include one or more DODAGs and a node may belong to multiple RPL instances. Next, we will talk about the DODAG ID. DODAG ID is the IPv6 address of the route. Next would be the DODAG version. DODAG version is the current version of the DODAG, and every time a new DODAG is computed within the same route, its version is incremented. Regarding the mode of operation, RPL supports two modes of operation. First is the storing mode. In storing mode, nodes keep routing tables for sub-DODAG, whereas in non-storing mode, nodes know only parent and do not keep a routing table. RPL communication takes place using ICMP v6, and the RPL control message is an ICMP v6 information message with the type of 155. Also, a RPL control message is identified by a code. Depending on the code value, the different types of RPL control messages are: first would be the DODAG information object, that is the DIO. DIO carries information that allows a node to discover a RPL instance, learn its configuration parameters, select a DODAG parent set and maintain the DODAG. Next is DODAG information solicitation, that is DIS. DIS messages are used to solicit a DIO from a RPL node. Its use is analogous to that of a regular solicitation of IPv6 neighbor discovery. Next is the destination advertisement object, that is the DAO. DAO messages are used to propagate destination information upwards along the DODAG. In storing mode, the DAO messages is unicast by the child to the selected parent. In non-storing mode, the DAO message is unicast to the DODAG root. Last is the destination advertisement object, that is the DAO ACK. So, the DAO ACK message is sent as a unicast packet by the DAO recipient, which could be a DAO parent or a DODAG root, in response to a unicast DAO message. So, to summarize RPL, it is an IPv6 compliant distance vector routing protocol, and an RPL instance consists of one or more DODAGs. DIO are broadcast downwards, DAOs are requests to join upward, DIS are DIO solicitations, DAO ACK are responses to DAO. Non-storing modes do not keep any routing table and send everything upward towards the root. Let us analyze the security concerns in RPL now. The RPL specification defines secure versions of various routing control messages as well as three basic security modes, that is unsecured, pre-installed and authenticated. There are a number of limitations in the conventional RPL security. Other than the secure versions of the routing control messages and the security modes, no further security mechanisms are designed in the current version of the RPL protocol standard. Considering that RPL already provides mechanisms to secure routing communications against external attacks, research efforts may be focused on the definition of threat models for RPL and also on mechanisms to protect RPL communications and operations from internal attackers. RPL is also susceptible to number of conventional routing attacks like the selective forwarding attack, black hole attack, sinkhole attack and other attacks typical to its operation like the rank attack, version number attack and many more. To conclude, we can say security is non-negotiable and research in RPL should try to address this through effective first and second line of defense mechanisms to ensure the integrity of the network under all circumstances. Our last protocol in this discussion is the application layer protocol, often called the web protocol for IoT, that is the CoAP, the constrained application protocol. CoAP is a specialized web transfer protocol for use with constrained nodes and networks in the IoT. It is designed and developed by the Constrained RESTful Environments, that is core working group of the IETF, specifically for machine-to-machine and IoT applications like smart homes, building automation, etc. Let us understand how CoAP was developed by the core working group. The communication on the internet relies on the fundamental representational state transfer, that is REST architecture of the web. REST defines architectural style for developing web services. The work in core working group aims at realizing the REST architecture in a suitable form for the constrained nodes and networks. Thus, the working group designed CoAP as an application layer protocol which is very similar to HTTP protocol of the conventional internet and follows the same request response patterns used by the HTTP. It uses familiar HTTP terms like GET, PUT, POST and delete methods, status codes, URIs, etc. For simplicity, we can think of CoAP as HTTP REST for constrained environments, that is with low memory, low power, low bandwidth and higher rate of packet failure. The specifications of CoAP core protocol are specified in RFC 7252. So far, we have understood that CoAP follows a RESTful architecture, allowing devices to communicate using standard methods. It's like having a universal language for IoT devices. But now, let us examine the design goals for CoAP. As was already discussed that constrained networks such as 6LoWPAN support the fragmentation of IPv6 packets into small link layer frames. However, this causes significant reduction in packet delivery probability. Thus, one of the design goals of CoAP is to keep message overhead small, thus limiting the need for fragmentation and minimizing the communication overhead. CoAP achieves this goal by using a minimal header size, compressing the HTTP and efficient message serialization, making it an ideal choice for resource-constrained environments. However, CoAP does not blindly compress the HTTP, but rather realizes a subset of REST common with HTTP to optimize it for IoT application. Thus, CoAP easily translates to HTTP for integration with the existing web. Instead of a complex transport attack, CoAP uses UDP on IP. A 4-byte fixed header and a compact encoding of options enables small messages that cause no or little fragmentation on the link layer. Let us now analyze the architecture of CoAP. Logically, the architecture of CoAP is based on the two-layer approach. First is the CoAP messaging layer used to deal with the UDP and the asynchronous nature of the interactions. And the second is the request response layer in charge of mapping requests to responses and their interactions using method and response codes. Let us look at the role of methods in CoAP. In CoAP, methods indicate the type of interaction a client wants to have with the resource on the server. CoAP supports the following methods. First is GET. The GET method is used to retrieve the current state or value of a resource from the server. It is a safe method that doesn't cause any modification on the server. Next is POST. The POST method is used to submit data to the server for processing. It can be used to create a new resource or trigger a specific action on the server. Next is PUT. The PUT method is used to update or create a resource on the server with the provided data. It replaces the current state of the resource with the new data. Next is delete. The delete method is used to request the removal of a resource from the server. It signifies the intent to remove the specified resource. Next is observe. The observe method is used to monitor the state of a resource over time and enables the clients to observe resources with a defined query, that is, to retrieve a representation of a resource. This method is not present in HTTP but only in CoAP. Next, we will see the message formats in CoAP. The four primary types of CoAP messages are CON, that is the confirmable messages. CON messages are used for reliable communication, ensuring that the recipient sends an acknowledgement. NON, that is non-confirmable message. NON messages are used for faster communication without requiring acknowledgement. And next is ACK, that is the acknowledgement. ACK messages are sent in response to CON messages to acknowledge their receipt. Next is RST or reset. RST messages are sent to cancel a pending CON message that hasn't been acknowledged. Now this figure shows a typical CoAP request response example where the CoAP client requests the resource from CoAP server like thermostat and the CoAP server responds with the thermostat reading. If we observe closely, the URI given in the figure, the prefix shows the name of the protocol, that is CoAP, the domain, that is my home, and the port number, that is 5683. The suffix of the URI depicts the name of the device, that is thermostat, and the parameter which the IoT device controls, which is temperature in the given URI. Now let us look at the similarities between HTTP and CoAP. With respect to request response model, both CoAP and HTTP follow a request response communication model. A client initiates a request and the server responds with the appropriate data or action. Now with respect to URI structure, both protocols use a common resource identifier, that is URI structure, to identify the resources. This allows the clients to specify the target resource in a standardized format. As can be seen in figure, both the protocols have similar URI structure and prefix, having protocol information and the suffix having the port and the resource information. With respect to header fields, CoAP and HTTP both employ header fields to convey metadata about the request or response. These fields contain information such as content type, cache control, and many more. Now let us look at the differences between the HTTP and the CoAP. In terms of transport protocol, CoAP is designed to work over the UDP, which is a connectionless lightweight protocol. This makes CoAP suitable for constrained networks and devices with limited resources. Whereas HTTP typically operates over TCP, that is the transmission control protocol, which ensures reliable and ordered communication. However, TCP's overhead can be unsuitable for the resource constrained environments. Now in terms of header size, CoAP headers are smaller than the HTTP headers, which is essential for minimizing overheads in environments with limited bandwidth and processing power. HTTP headers can be more extensive due to their additional metadata and features, which can be insufficient in the constrained scenarios. In terms of efficiency, CoAP is designed for efficiency in constrained environments. It supports features like tokenization, which allows lightweight state tracking, and observe, which reduces the need for frequent polling. While HTTP provides more features and flexibility, its overhead and connection oriented nature can be less efficient for IoT devices and constrained networks. In terms of reliability, CoAP offers optional reliability through confirmable messages where the sender receives acknowledgements for the sent messages. HTTP operating over TCP inherently provides reliable communication with ordered delivery of messages. Now in terms of usage and scope, CoAP is specifically designed for constrained networks and devices, making it well suitable for IoT applications where resources are limited. Whereas HTTP is widely used in traditional computing environments and the web. It is more feature rich and suitable for scenarios where robustness and reliability are essential. Now let us look at the security considerations of CoAP. CoAP is currently defined only for UDP communications over 6LoWPAN. Although the adoption of transport layer approaches such as the TCP is still open to debate, but with the ongoing research addressing the adaptation of TCP for 6LoWPAN environments. Regarding security, CoAP adopts DTLS, that is Datagram Transport Layer Security at the transport layer to transparently apply security to all the CoAP messages in a given communication session. DTLS provides guarantees in terms of confidentiality, integrity, authentication, and non-repudiation for application layer communications using CoAP. However, the following challenges still need to be addressed in the context of CoAP security. The impact of DTLS handshake for authentication and key agreement can pose a significant impact on the resources of constrained devices. Thus, investigating optimizations for DTLS in IoT is still needed. And the lack of appropriate key management mechanisms for the support of secure CoAP communications. Amplification attacks, IP address spoofing, and cross-protocol attacks are also possible in CoAP. Thus, we must implement robust security measures to ensure secure communications in the Internet of Things. Finally, as we wrap up our exploration of 6LoWPAN, RPL, and CoAP, it's clear that these protocols are the backbone of IoT communication. Their unique features, relevance, and the importance of implementing robust security measures make them indispensable for the seamless functioning of a secure, reliable, and an interoperable Internet of Things. Thank you.